Hey, my name is Kahing. Today I'm here to tell you about the arc length in calculus. In this section, we are going to look at computing the arc length of a function. Because it's easy enough to derive the formulas that we will use in this section, we will derive one of them and leave the another to you to derive. We want to determine the length of the continuous function on the interval. Initially, we'll need to estimate the length of the curve. We will do this by dividing the interval up into n equal subintervals, each of white, and we will denote the point on the curve at each point by p. We can then approximate the curve by a series of straight lines connecting the points. Now let's generalizing the arc length. Now let's get a better grasp on the length of each of these line segments. First, on each segment, let's define. We can use then compute directly the length of the line segment as follows. Sigma k equal to 1 square root delta x squared plus delta y squared. By the mean value theorem, we know that on the interval there is a point, so that we can write delta y equal to delta x f prime x. Therefore, the length can now be written as sigma k equal to 1 square root delta x squared plus delta x k f prime x squared. Actually, just substitute the delta y into the equation. We can get the exact length by taking n larger and larger. In other words, the exact length will be limit n approaches to infinity and k equal to 1 and 1 plus and square root 1 plus f prime squared. The exact length of the curve is then integrate from a to b square root 1 plus f prime x squared. It also can write to a second form, which is integrate from a to b square root 1 plus dy dx squared. The square root, don't get too confused. With one we differentiate with respect to x, and with the another we differentiate with respect to y. One way to keep the two straight is to notice that the differential in the denominator of the derivative will match up with the differential in the integral. This is one of the reasons why the second form is a little more convenient. Okay, before we work any examples, we need to make a small change in notation. Instead of having two formulas for the arc length of a function, we are going to reduce it in part to a single formula. From this point on, we are going to use the following formulas for the length of the curve. No limits were put on the integral, as the limit will depend upon the L that we are using. Using the first L will require x limits of integration, and using the second L will require L limits of integration. Thinking of the length formula as a single integral with different ways to define L will be convenient. When we run across arc lengths in future sections, also this L notation will be a nice notation for the next session as well. Now that we will derive the arc length formula, let's work some examples. Example 1. find the arc length of the arc of fx equal to ln sine x. In this case, we will need to use the first L since the function is in the form. So let's get the derivative out of the way. The equation is f prime x equal to cos x over sine x also equal to cotangent x. Let's also get the root out of the way since there is often simplification that can be done and there is no reason to do that inside the integral. So we can get in the equation cosecant x and the arc length is then L equal to ln square root 2 plus 1. Okay, let's move on to example 2. Find the length of the arc of the semi-cubical parabola y square equal to x cubed between the point 1, 1 and 4, 8. In this case, the function and its derivative would be dy dx equal to 3 over 2 x root square root x. The root in the arc length formula would then be L equal to integrate from 1 to 4 and square root 1 plus dy dx squared. And just substitute the dy dx into the equation, we get integrate 1 to 4 and square root 1 plus 9 over 4 x. And we also don't forget to use the substitution method. We deem the u equal to 1 plus 9 over 4x and du equal to 9 over 4 dx. And when the x is equal to 1, u equal to 13 over 4. And when the x is equal to 4 and the u is equal to 10. So substitute the answer inside and we finally will get the arc length is then 1 over 27 and times 80 square root 10 minus. The standpoint in the integral in the previous example was not that difficult. It was just a calculus 1 substitution. However, from a particle standpoint, the integral was significantly more difficult than the integral we evaluated in the example 2, in the example 1. So the moral of the story here is that we can use either formula. However, one will often be significantly easier to actually evaluate. Okay, now let's retry the third example. The question is find the arc length functions for the curve y equal to x squared minus 1 over 8 ln x, taking the p 1 to 1 as the starting point. And we differentiate the both sides and we get f prime x equal to 2x minus 1 over 8x. And then we use the completing the square to make the 1 plus the f prime x squared to be 2x plus 1 over 8x, the whole thing squared. And then we substitute the completing the square inside the formula given, and then we can cancel the square root and we get the integrate 1 to x and 2x plus 1 over 8t. And the answer we can get is x squared plus 1 over 8 ln x minus 1. Because we don't know, the question wants us to integrate the interval from 1 to 1. So I just deem the x as the interval. Last, we are going to try the last example, which is the hardest example, the example 4. Determine the length of x equal to 1 over 2 y squared for the interval of x 0 to 1 over 2. Assume that y is positive. We will have used the second L for this one, as the function is already in the correct form for that one. Also, the other L would again lead to a particularly difficult integral. The derivative and square root will be then. So we just take the x, plug into the equation, that we were given x limits and we will need y limits for the L. With the assumption that y is positive, they are easy enough to get. So we can get the L equal to integrate from 0 to 1 square root 1 plus y squared dy. And then we must use the trigonometric substitution. We deem the y equal to tangent theta and dy equal to secant theta, secant square theta. And when the y equal to 0 and the theta equal to 0, when the y equal to 1 and the theta equal to pi over 4. So we just substitute the equation inside the formula given and we get the secant theta. And finally we get the equation L equal to integrate from 0 to pi over 4 secant cube theta d theta. And we substitute the value inside the equation. Finally we will get the answer 1 over 2 times square root 2 plus ln 1 plus square root 2. So now